Hello everybody, welcome back. So in today's episode, we're going to be looking at improving on our vanilla Grafana and authentic server. When we first built out the Grafana server, it was all vanilla. We left it as is. We built it and it was ready to go. There are a number of vulnerabilities that we want to test out. And from those tests, we want to see what an attacker would do if they had that information and what they could do. Keep in mind that the vulnerabilities and the attacks and the hardening are all documented on olpsgolden.com, where you can follow along with everything from the build it, prove it, to the break it, and then a following article that will show how to fix it and validate it. The whole goal is to harden our system so that the attacks that I show here cannot be done. So our next step is to validate that our Grafana, Prometheus, and Exporter server is still alive. Keep in mind, just like our previous video, they're all living on the same server, but in different containers. So that being said, we've created a variable called Grafana with the IP of that server of 75.109. From here, we are going to do a service availability check, and we're identifying the HTTP code that will be returned. Hopefully, it'll be at 200. If there's a 401, it means that the IP is not available or the port is not listening. And then here we are identifying the variable again, since again, Grafana, Prometheus, and the exporters are on the same server, the port, and then a URI that we'll be checking to make sure that it is alive or not. You'll see here that we have a third service called OpenBow. OpenBow is a HashiCorp Vault fork that occurred on version 1.14. In this exercise, once we find the vulnerabilities, eventually we'll be moving the secrets from our environment file to OpenBow so that it's in a secure system instead of it being on a local server. So here we see that, again, we have our local jump server IP is. We're identifying that our Grafana Prometheus servers with the ports, they're all active with 200. Again, if this did not work, this would have came up as 401. And then we just have seen that OpenBow, it's initialized and it's not sealed at the moment. So everything is functional and it's ready to be used. So the next thing we're going to check is validating to see if Grafana has the default admin credentials. So admin is the username, admin is the password. So again, we're identifying the variable of Grafana, which is going to be our IP address ending with 75.109. We're identifying the user and password, just seeing if we can get in with the admin settings using the credentials. So as we can see here that the admin is not accessible. Like we checked before with the initial setup, is that the IP is responding, but we just validated that the admin credentials are not working. So from here, we do have the admin credentials because we're using this as a home lab and testing. So we're identifying the super secret password of temp password 1 exclamation. We're identifying it and then hitting the variable Grafana again. And let's see what the results will come back with. And it came back with a 200, meaning successful. So we just validated that, again, admin is not set, right? Because we changed the admin password. And the admin password is the super secret password. And we just validated that it all works. I would consider this a vulnerability because, one, even though we know the password and this is a home lab, this is a very weak password and we'll be changing this later on. Keep in mind, this will all be blown away at the very end of this lab. So now that we know what the admin password is, let's make that a variable. Our next thing we're going to do is test to make sure and see what we can pull from the admin API and see if there's anything of value knowing that we have the admin password. again, the variable of the admin password, Grafana, the admin API. We're basically going to see what we can pull down and what sections we can pull. So the sections we can pull is default, alert. This is a full breakdown of what we can pull. This is pretty wide open. On here, we can tell that we can pull basically alerting, auth, database, security, everything. This is a treasure trove right here. So if an attacker got access to the admin password, this is at a base level what it's going to pull from the admin API. So there's multiple things that we just validated. One, admin is not being used. Admin and a weak password is being used. And from that weak password, we can see that an attacker can basically see everything within Grafana and query the admin API. So the next thing we're going to test out is Prometheus. By default, it has no authentication at all. Anyone on the network can query it and get a complete map of the infrastructure. Host names, kernel versions, every service, it is a smorgasbord of information. So let's query it and see what we can get. So what we're doing here is that we're basically querying Prometheus, and the node uname info is a metric that Node Explorer collects from a Linux uname command. We're basically asking Prometheus, tell me about the host you're running on. It hands back the host name, kernel version, and CPU architecture. And that's where these items on the grep on the very end is identifying. Again, the node name, release, and machine name. So we can see here from the results is that our processing architecture is going to be x86 64-bit. This is the container ID. The kernel release that this is running on is Debian 13 running on an AMD 64 architecture. Next, let's see what else we can pull from there. Every service it monitors with an internal URL. So basically this is going to hit the API and we're going to be scraping and pulling any information with what it's monitoring and what is the internal URLs. So what do we have here? We have a free network map here. 5 services, 1, 2, 3, 4, 5, yep. Internal host names and ports with no credentials needed. Nice. So this is one of the things, again, since there's no authentication on Prometheus, this is kind of what you can pull. The next thing we're going to do is try to pull and see Prometheus. How is it configured? So again, we're doing a curl to the API and we're pulling basically anything that has a YAML file or a data file, anything that we can pull that can give us some good idea on how it's configured. So we just validated what we can pull from Prometheus. There is a smorgasbord of information that is very usable. We've identified what kernel is being run on there. We know the container ID, what's being pointed to or scraping the URLs and pointing to Prometheus with the ports. And we just scraped the entire basically the config dump. And from here, we can basically plan, or an attacker can plan on how to utilize this information to infiltrate or break the system. So let's think like an attacker. And let's go deeper. Let's count how many metrics are available and pull the container inventory. For this command, we're going to see about counting every unique metric name Prometheus has. Let's show the sheer volume of data an attacker can query. Oh wow, 1,112. That's a lot. And keep in mind, all of that is queryable. We can query up to 1,112 metrics. That is insane. So this command is going to pull everything from cAdvisor's container last seen, as defined right here. And we're going to pull that metric through Prometheus. This will show every container and what image it's based on. At this point, the goal is for the attacker to get the full Docker inventory without touching the actual server. And look at this. We can tell that there are 5 containers. So now we can tell what is fully running on the server, which is 5 containers. 1, 2, 3, 4, 5. Yep, 5. Plus an additional 1,111 metrics, which is still a whole lot. So what we have proven here is that if a Prometheus server is unauthenticated, it is queryable. And depending on the level of hardening, we can query as much metrics as possible, given that it is unauthenticated. And knowing that there is 1,112 metrics that we can query, that is more information that an attacker can use and definitely infiltrate further in your system. cAdvisor monitors resource usage. It has its own API on port 8080, completely separate from Prometheus. So let's see what it hands over. Actually, let's clear this up. This is basically your hardware spec of what cAdvisor sees. And it's just another way for an attacker to see more information and where a potential target can be. This command basically pulls real time what the usage is of our container. And what this does is that it gives us an idea of the capacity of the container, and an attacker can find out if it's in high load, do we want to be chaotic and take that down? Or if it's low usage, can we silently get onto that container and do continual reconnaissance on the environment, the system? So that is kind of something that they could take advantage of. Both scenarios they can take advantage. If they want to be chaotic, they can bring it down. If they want to be silent and observing, they just put a small app on there and observe and try to gather more credentials or more information, or do more recon and use that as a jump to other trusted environments. So let's clear this up. So next, let's take what we found with cAdvisor and let's expand on that. What would an attacker continuously look for? Our goal here is to pull Docker daemon info and pull additional detailed container information, such as image names, labels, creation times, what have you. Woof, woof. Look at this. Even cAdvisor is dumping the host system services too, not just the Docker container. Wow. So we just validated with this scan that the containers endpoint is responding and stats is responding. So let's see here. We found our container ID service. We see the cron service. We see our dbus service. We see slice docker.services, this is basically the daemon. So we now know what system services are currently running. Let's pull some more metrics. Now, let's see about pulling just the Docker containers themselves, not the systems. What this command does is it filters the metrics for actual name containers and basically cutting out the system noise, which is we're identifying the naming right here. Okay, we found our 5 containers. So we went from the system down to the container. cAdvisor exposed from one endpoint, it showed the hardware, the Docker containers, or our 5 containers, what host system services are running, which is that container D, cron, dbus, and what our real-time stats are. So this is pretty cool. This is all unauthenticated. The attacker gets both the hardware inventory and the full software inventory from one port. Nice. So the next thing that we're going to check is Blackbox. Remember that when we first started this, we did a scan and saw that Blackbox Exporter was connected to Prometheus. So let's check that. But before we do that, what is Blackbox? The whole point of Blackbox is that it monitors endpoints from outside the network. So you can add a URL, and it basically checks, can I reach it? Is it responding? How fast is it going? It can do anything from an HTTP check to DNS, TCP, and ping. Basically, is my website up? Yes or no? Is the API responding? Yes or no? That's what the intention of Blackbox. So the problem with this is that Blackbox, since it checks everything outside the network or inside the network, if an attacker gets access to it, it can point to any URL. Think about that. Any URL. That can be very concerning. So let's see if we can force it to probe somewhere. So on here, we're testing if it can do a cross-VLAN connection, and we're basically querying Blackbox with the Grafana IP with 9115 or port 9115, which is Blackbox, and it's going to probe this IP, which is our authentic server, and see if it's even active or not. So we just validated that this Blackbox exporter can hit our authentic server. So from here, we just validated that we can jump from Blackbox, do a cross-VLAN communication from itself to another server. In this case, it's going to be the authentic server. Now that we know that Blackbox can communicate to authentic to another VLAN, let's see what else we can probe from Grafana to authentic using Blackbox. So in this case, we're going to validate that the attacker can use Blackbox to scan multiple ports and endpoints on authentic, mapping out what services are running, in addition to what features are actually turned on in authentic. The main page, the admin API, is there authentic outposts enabled? These are all things that we want to look at and validate. So the first point we can point out is that the main page is going to be accessible via port 9000 for HTTP. The admin API, same thing, but we're identifying the URI of API version 3. And then the authentic outpost is going to be on a unique port of 9300. So let's see what we get. So what do we find here? We have just found that we can hit the main page with the status code of 200. We can also validate that the API is running, but couldn't find the actual endpoint. But we just validated the API is accessible. And also that the authentic outpost is not running at this time or is not exposed, one of the two. So as an attacker, the service for the API is accessible, but it may not be turned on or not found. Then you just continue scanning and you try different variations to scan and see what the results are. This is a very good finding so far. So from here, we can validate that we can get to the main page because we have a status 200. We validate that the API is listening, but it's not the right path. And the authentic outpost is either blocked or not turned on whatsoever. As an attacker, there's a few things that you can look here. One, since we can get to the main page, that's a vector that we can definitely attack on. Even though we can confirm on the API that the API service is turned on, the path is different. So we just have to continue scanning and find out what different ways to access the authentic API. And at some point, we will get in. And another thing we validate is that we can, again, cross VLAN communicate to authentic, which is a big boom for as an attacker. So let's clear this up and move on to our next vulnerability. So the next thing we're going to work on is our OAuth secret in plain text. If you remember back in our first episode, we saw that we basically stored our secrets in a environment file on our Grafana server. And now we want to test that out and see what can we see on a client side or from the jump server. Is it still viewable? What would the attacker do to get more access to the server and try to see the OAuth secret? So the first thing we're going to do is try to pull the Grafana config and see what is in there. Can we pull a client secret in the whole mix? We'll display the client secret. So here, again, we're identifying our variables. We have the admin password, the Grafana variable, And then we're identifying grep anything that comes in that says client secret. We were able to pull in the config, but as you can tell here, it may, even though the secret is starred out, we have validated that the secret is actually on the Grafana server, not stored in a secret vault or anywhere. So this is actually very good for an attacker point of view, that we're able to see that things were stored on the server itself. So the next thing we're going to do is basically jump on the Grafana server and see what we can find. We're now on the Grafana server and we're going to do a cat and see, one, can we see the environment file? And two, is there a secret or a password or a token stored on that environment file? So as we can tell, there is a client secret stored on the environment file. So what we just validated is that we can see the secret on the server itself. And if a user has the owner access, they can see this file, which is really concerning. So next, we're going to try and see if we can find the secret in the container itself. So we're identifying, we're going to go execute within the Grafana environment and look for anything that might say client secret. In addition, we're going to inspect the container to see if there is a config.m file, and if there is there a secret involved in it? Or is there a secret in the metadata in the environment? So there is. We can definitely see, inspecting the container, we can see that there's a secret in the environment itself. And when we inspect the metadata, we can definitely see the secret again. So this is not good. The goal would eventually dump this into a secret vault and let there be a lookup from Grafana to the secret vault. So now let's jump back to our jump server and see what we can do with the information we have, and see if what an attacker possibly would do with this information. So now that we have all the information we need for this vulnerability, and yes, there's probably more we can do, but for this exercise, we're just going to take the information we have, and now we're going to utilize that and seeing what more can we pull, what can we actually do to the Grafana server from the jump server. So at this point, we have gathered all of our information, and we want to start utilizing that information to see if we can pull more data from the Grafana server, and can we infiltrate using that information. So with this, we're identifying our two variables again, which is our IP address ending with 75.109. Then we're actually identifying our admin password again. And then we are doing a curl, which is going to reach out and utilize the admin and then the variable admin password, and then the admin API on the Grafana server. From here, we're going to pull in a giant config, and then we're only going to pull in things that actually show content as defined down by. So from here, there's a few things we can pull. We know that the API, here's our authentic API. We can also identify we're not doing auto login. The Grafana client is definitely being used on the server. Basically, an environment file is being used. We still can't see our client secret. And at this point, I mean, this is pretty good stuff. I mean, identify there's additional groups. There's Grafana admins and admin and viewer. So far, this has been a good haul. You can definitely see what fields are actually displayed, and also where are we going to be authenticating. Also, we can also identify that the authentication server is on a non-secure port. So this is very good findings. Next, let's try to see let's see if we can pull every secret in the config and see if we can pull in the secret. So with this new script, we're doing the same API call, but this time we're going to look through every section in the config, database, auth, security, SMTP, everything, and see if there's a secret, a password, or a key printed in those configs, and if they're not, encrypted already. So can we see those contents right there? This can catch anything from admin_password, client_secret, secret key, API key. So this would be, if anything comes up here, this would be a great haul. So here, let's break this down a little bit. So one of the things we can say is that a few things. The admin password's on there, but it's definitely hidden. The secret key is hidden. Let's see here. SMTP password is empty, so that is not good. Our database password is empty, so that means it's running on a default no password for root. That's not good. And password policy, there isn't a password policy there, but it is hidden. So at this point, we can definitely say that though things are hidden, we now know that there is an environment file on that server, which is a key target to aim for. In addition to, the passwords are set on there, but they're hidden. In addition to, there's a database server with no password key on there at all. So if it's default, then it could be root and no password, which is a huge vulnerability. In addition to, we can also say that when we were on the Grafana server, not only can we see the secret in the file, we can also see the secret in the container. In addition to looking through the metadata, we can actually see that as well. So all in all, there's a lot of things that we need to fix on the vanilla Grafana server, and that's something we can do when we go ahead and fix the issue in the very end of the video. Let's clear this up, we're going to move on to the next vulnerability. Here's a scenario for our vulnerability here, and that is someone gets let go and you disable their account and authentic. How long will their access last? They should be disabled immediately on Grafana, right? But here's the issue. Grafana sessions are cookie based. Once you're logged in, Grafana never checks back with authentic to ask, is this user still valid? If there's no session timeout, that cookie can work on forever. So our goal here is to see what is the default values on Grafana to see how long will that cookie last. So once again, we're going to identify our two variables, which is the Grafana and admin password. And then we're going to use this script and see what can we pull within the Grafana config for auth. So here's our script. And so what are we doing? We're doing a curl, and we're going to use our admin and our admin password. We're going to hit the Grafana server with port 3000, and we're going to the admin API. We're going to go and grab anything that's related to auth in the config, and we're going to focus on what's the lifetime, what is our timeouts, what's the rotation. Basically, we're pulling anything that's related to the life cycle of the session cookie. So from here, we can identify that our maximum inactive lifetime is going to be 7 days. The maximum lifetime is 30 days. And the interval is every 10 minutes. So one of the things we can take from this is that the longest inactive duration we can have is 7 days, and the maximum lifetime duration is 30 days. And the token rotations every 10 minutes, but that does not mean the session is going to close itself. It will persist. So let's say a user leaves, or you have a user that you're testing in your home lab. If you disable that account or delete that account, that user ID will have continual access for 7 days. That session key will maintain itself for 7 days. So they'll still be active. So let's prove the sessions actually work remotely. So now let's actually grab a session cookie on this jump box and see if we can prove the sessions actually work remotely. So we're going to use a user called Dingo. You may remember him from our previous lesson. Next, we're going to go to Developer Tools. And now we're going to go down and make sure you go to Applications, then your Storage, and then all the way down to Cookies. And then we're going to look for our cookie values. Okay, from here, we're going to break this down and we're going to try identify the cookie here. We're going to go to the Grafana API or admin API, and then we're going to try and see if this cookie works. And look at that. We are able to get in. Is the user a Grafana admin? Nope. But we can definitely use the key. Now we're going to go and disable the user. And now that user is disabled. So now let's test this out once more. Now that the user is disabled, we'll see if the token still works. It does. So look at that. So we disabled is see there? So one of the things we validate is that Dingo is disabled and we can still have access to the Grafana server. So let's double check our work right here. So Dingo is disabled. And we can still get to the server here. Now let's see what would happen if we go here onto the Grafana server. And can we still browse around? Yep. So we just validated that the user, see Dingo? So the user still has access, even though he is disabled. He or she, whoever Dingo is definitely disabled, and he still has access. Another key point that we can look at here, we disabled Dingo on Authentic, but Grafana doesn't even know about that. Why? Because the cookie will stay in process for at least 7 days. So that this disabled user still has access for at least 7 days. So now that we have seen this, you should be good to go. So the next part is to see how an attacker or a bad user could utilize this when they're not supposed to have access. What can they actually do? Let's clean this up. Okay, so our next step on this vulnerability is to see how an attacker would utilize this. So on here, let's break this down a little bit. So in this, we're going to do a curl. We're going to hit the organization's user API endpoint. And hopefully we're going to return a list of every user in the current Grafana org, names, emails, and roles. We have our Grafana session cookie, and we're going to actually print out in JSON response so we can actually read it. Okay. So on here, we just validate that there's an admin at localhost. There's an admin at lab.local that's used for authentic default admin. And we just identified Dingo. So one of the things we can say here, not only of the users that we've seen, but we're not even using Dingo. We're actually just using the session. And so think about that. If you're going to do a grab to a Grafana server, you have the session cookie, but you don't have the user, and they're still making connections and it's still active, even though it's a disabled user. This user has access to preview your environment, depending on the permission that it has. In addition to, we can see that Dingo is actually set as an admin, which is actually very good for us to know. So from here, we're going to try to see what we can do with that session ID. We now know that the user has admin access, so what can we do here? So we're using Dingo's session cookie to create a new admin level service account with a persistent backdoor. Now this is pretty extreme, so if an attacker or a user has admin access and they get disabled and their session is still active, they could create a service account with a persistent backdoor, so no matter how many times you reboot it, it will still be there. And this could be considered a hidden admin level access right here. So breaking this down a little bit, so we have our curl and we're pushing information in onto Grafana's API, admin API and for the service accounts. In addition to, we're utilizing the cookie from our previous session, and we're going to give it a name of persistent, backdoor, and admin, or a role of admin. In addition to, we're now identifying wherever is being published here, we're going to save it into our SA response variable that we can call up later. So as you can tell here, it looks like our session cookie rotated. Remember, it rotates every 10 minutes. So let's see about grabbing another one. So let's update this. Okay, this one we utilized the updated cookie, and then we just create our first backdoor, first service account backdoor, and it has admin access. So now we really don't even need to use the Dingo credential or session cookie. So now we can just use the service account with our backdoor. So now let's see about our next goal. Even though we have a service account, let's see if we can create a permanent API token associated to that service account. And there we go. We just created a new token. So we just validated that we now have a new permanent key that we can reutilize. So let's test it. And it works. We were able to get in. We don't need Dingo's key anymore. So now let's remove the backdoor service account, because we just have the API key. We don't need the service account. We now have a key that will stay active even after Dingo's session token is gone. Service account is now going to be deleted and not needed anymore. So now, so let's review for a second. So we just validated that we have a user called Dingo that was able to log in. We now know that the key will reset itself every 7 days for a maximum of 30 days. So if someone's logged in and their account gets disabled via their authentic server or an IDP, then at that point, their session is still live. Grafana doesn't know to check back in, except for checking back in 7 days. At that point, they have free reign to grab an updated session token, so they can use that session token, as we show here with the browser, and they can use that to, depending on the level of access they have, they can utilize that token to see about creating a service account. Once they create that service account, then they can create a API key. Once that key is created, they just got to delete that service account that they just created. And then at that point, there's an API key available and the service account is gone. So at that point, there's a backdoor that they will utilize to continually be in your system. So for our next vulnerability, in vanilla Grafana, there is no really rate limiting whatsoever. So there could be a possibility of a brute force or DDoSing, basically overloading the system and basically blocking any further connections. Let's test out and see what it looks like from Grafana if there's a bad login attempt. So on here, we're basically sending 10 login attempts in a row that has a wrong password. As you can tell right here, wrong password. If all 10 come back instantly with a 401 and no delay or lockdown, there's no brute force protection. That could be really, really, really bad, because if there's none, then this is a field day. An attacker can just go here and just run thousands upon thousands requests within a few seconds and it'll overload the connection. And we just validated that there is no rate limiting because we just sent 10 bad logins and we weren't denied at any point. We still continued, got 401. So now let's see if there's any rate limiting headers that we need to be aware of. This command checks to see if there's any HTTP response headers for anything related to rate limiting. If there's nothing that comes back, Grafana isn't even aware of rate limiting at this point. There isn't. So vanilla Grafana does not have rate limiting turned on by default. So our next step is to see about utilizing the information we got regarding knowing that there isn't a rate limit. So at this point, let's see if we can do a brute force and see if we can guess the admin password. We're going to pretend we don't know it, and we have a set of passwords we can utilize to see if we get a hit or not. We have found that of the 5, 1 hit with temp password 1 exclamation. All the others came back, so we have a hit. So this is good. So we just did a brute force and found a password that we can use. In addition, knowing that we associated this password to an admin login. So now, if attacker knows the admin and the password, they can create, again, another backdoor. So what is this? We've identified the admin password that we just discovered. It's hitting the admin API to create a service account with the admin and the password. And we're going to give it a name. The service account is going to have a name of monitoring-svc. The role is going to be admin. And we're echoing saying that the service account ID is, we're going to print the information into this variable of SA_ID. We're going to be generating a permanent token so that even if the admin password changes tomorrow, the token will still live on forever. And we gave the name of the service account here something very minute, monitoring-svc, or in some cases they would just call it service. This is a very innocent name, and let's see what we get. Okay, so we have created a permanent backdoor with the cred with the service ID of 7, and our permanent token is this right here. Now let's prove that the token actually works. And then from there, let's remove that backdoor. We're gonna validate that the token works without any credentials, and then we're gonna clean up the backdoor, and as if we were never there. So again, we're utilizing the token. Then from here, once we validated, we're gonna be deleting that backdoor. Okay, that backdoor, that service account has now been deleted. We now have our API key that we can continuously using that has admin cred. Very nice. So for the next vulnerability, we're going to be testing the Grafana Prometheus containers and find out if there's any hardening required. Now, I will point out that we will need direct Grafana access to test this out. So we will have to SSH onto our Grafana server and apply some of our vulnerability scanning. This is very important because even though we tested a number of our capabilities and vulnerabilities on the jump box, we also want to jump onto the Grafana server itself and see if there is any ways to harden the containers themselves, which is very important in security because we don't want to just assume the traffic is going to secure everything. If at any point that someone gets onto the Grafana server and they have access, how hardened is our configuration so that they can't see any of the additional configurations on board. So let's log on to our Grafana server. So what we're looking for is whether the Grafana container has any security restrictions. Is there going to be capability drops, privilege escalation prevention, resource limits, basically anything that we can lock it down so we give limited accessibility for anyone who has a reader access or anyone who just logs onto the server. Are we going to make it more difficult to see the config itself? So what this is doing is we're going to do 4 things. Are any explicitly added? is there anything in security opt that we should be aware of? Privilege. Is the container running in privilege mode? Let's run it and see what we get. So let's decode the bit mask right here. What this does is translates the hex number into human readable capability names. So it basically shows exactly what the container is allowed to do if the process inside requests it. Wow. So, so there are 11 capabilities within this container right here. In reality, there should only be 3 or 4, but if an attacker gets access to this container and gets inside the container, it has free ride to do as much damage as possible. There's no limitations to what an attacker can do if they get inside the container itself, because this is darn near almost admin right here. Very concerning, and we'll clean this up when we get to hardening our environment. So the next thing we're going to do is, as you can tell, we are not using HTTPS whatsoever. No TLS, no nothing. So let's validate if TLS is even turned on. The open SSL, we're just basically trying to make sure that TLS, if there's TLS even turned on. If nothing is listening, we get a connection refused. Our next is we're going to curl Grafana and look for any HTTP response headers that Grafana may have. Strictly speaking, strictly transport security, which forces browsers to use HTTPS. We're going to be looking for X-frame options, which prevents clickjacking, and X-content, which prevents MIME sniffing. If none of these exist, the connection has zero protection. These are things that the attacker cares about seeing from the Grafana server, and if TLS is even turned on, and also if the header options are even available. So the first thing we notice is that the port 443 has been refused. 302, so the redirect. So 302 is just a redirect from HTTP to HTTPS. And we can validate that there are a few options within Grafana with our headers. You can tell that X-frame options is deny, X-content, it has no sniff. But the critical one that we really care about, one that's not even showing, which is strict transport security. So let's also check to see if there's any cookie security. We kind of checked this earlier, but let's test it again. So again, we're doing a curl to the Grafana with the login page, and we're grabbing, looking for anything that has set cookie. Well, the good thing is that no set cookie header is not set on the login page. Cookies get set after the authentication, which is a good thing. That's fine. The point still stands though. HTTPS is not turned on, which was refused. There is no HSTC header, which is required with HTTPS. That's missing. And the transport is still over HTTP. This is wide open. One of the things we can do is that now that we know that the traffic is not encrypted, it's through plain text, we can look at this and see how an attacker would go about grabbing your credentials, unauthenticated credentials, through the wire. This is very important because whether you have a man in the middle or whether you have an attacker on a host looking at containers for the traffic leaving the container, one of the things we want to see is what do they see and how can they decode that information when there is authenticated traffic traversing via HTTP. So one of the things we're going to do here is we're basically going to be trying to authenticate through our admin and our password and encoding via base 64. This is exactly what happens on every authenticated HTTP request. And then at the very bottom here, we're going to see that we're going to decode the base 64 once it's been received. So one of the things that we got here is that here is the encoding of the admin password. And because we have a -D with decoding, this is the password and the username and password. This translates to both the username and passwords, not just password, it's both admin and password. So once again, we see that when we traverse traffic that's unauthenticated, there are ways to see both the user ID and the password. So in conclusion, we can say that we know the admin password because we have unencrypted traffic right here. The OAuth token exchange is plain text between Grafana and Authentic. So now that we've gone over 9 to 10 vulnerabilities and how an attacker could continue utilizing those attacks, let's take a step back. So one of the things that we can say is that there are a number of vulnerabilities that we have found so far, but in my documentation on oathsgolden.com, I have over 15 to 16 vulnerabilities. So we're missing about 5 or 6. To cut time, and at this point, we're almost at an hour with this video. I'm going to stop the video now. If you want me to demo those other 5 to 6 vulnerabilities, please post it in the comments, and I'll create another short video. But until then, I'm going to close this session out, and in our next video is to find ways to harden the environment, which is a very important thing that we want to learn since we now know what the vulnerabilities are and how an attacker could utilize those vulnerabilities to further expose the environment. So keep in mind that this is a home lab environment. At no time should these be used in a production in a real-time environment. This is purely home lab, purely development. Everything is locked down for my environment only, and it should be locked down to your own home lab environment only. So until then, stay paranoid, keep learning, and I look forward to seeing you next time.